Hello everyone and welcome back to the channel. Happy Valentine's Day to those who celebrate. I personally am pretty amped because I used a reservation bot to book my dinner reservation for tomorrow night. And as a result of that, this is probably the first time that me being able to code in life has ever impressed a woman. So good for me. Besides that, for those of you familiar with the game, I'll be attempting an internal transfer in my relationship this weekend from a front-end engineer to a back-end engineer. So wish me the best, but we're going to have to see how this goes. Anyways, let's go ahead and talk about DynamoDB and cover this paper. Alright everyone, this is like attempt 4 trying to record this video now. I've been having just really bad camera issues. You can see I'm trying something new with basically using PowerPoint plus writing at the same time, so you guys don't have to read my shit handwriting and I can use a red outline, but it just has not been working well. So I'm going to try and go through this thing as quickly as possible because I'm just praying that it works. It has been really frustrating. Basically, DynamoDB is a paper out of Amazon in 2022. It is not equal to Dynamo, and we're going to go into the history momentarily. The idea here is that in 2007, Dynamo came out. We covered that on this channel, and the main idea there is that we're getting a ton of availability through leaderless replication, right? We build that for the card service, and a lot of people end up using it for a variety of different applications. That being said, you have to self-manage that database, which is bad because your team developers have to do a ton of operational work on actually maintaining it, and you just don't want to devote your resources to that. So around the same time, SimpleDB and S3 are released from Amazon itself, and basically the idea there is that those are going to be completely managed by AWS, and as a result they are very popular. So basically SimpleDB is going to limit their table sizes to 10 gigabytes, and they have indexes on every field, which makes it pretty impractical to use, yet at the same time Amazon saw it still had a ton of traction within the company. So they basically wanted to create DynamoDB to combine the benefits of both. So one of which benefit is going to be the fact that it's basically infinitely scalable, so you don't have to manage your own hardware and move partitions around, while at the same time kind of keeping that great data model that everyone loves and consistent performance. Speaking of the data model, let's go over it very quickly. It's just like Cassandra. Basically, you've got a partition key and a sort key. So the partition key is going to make sure that all records with the same one belong to the same partition of the table, and the sort key is optional, but it's how we actually sort messages within those partitions. Okay. Quick message on the actual high-level architecture of this thing. Basically, we've got a client over here. The client is either going to make a GET or a PUT request for a given key and value, and so that's going to go to the request router. The first thing the request router is going to do is authenticate it. Then from there, it's going to figure out what storage node the key actually belongs to using some sort of consistent hashing functionality, and that is going to belong to the partition metadata layer. Now, this information ideally is going to be cached on the request router, but if it's not there, that's where we fall back to. Additionally, it's got to perform some sort of rate limiting, right? Because maybe this partition is getting too many different requests, and maybe in addition to that, the storage node that the partition is on is getting too many requests. So that is what global admission control is responsible for. It is keeping track of the requests going everywhere and basically reissuing tokens to the request router to try and actually follow and respect that. Finally, we've got our storage nodes over here. This is really the main part of the system. Storage nodes are going to be holding a B tree and a write-ahead log, probably in a solid state drive, and they're going to be replicated over different availability zones, where availability zones, as we've covered in the past, are just different data centers, albeit in the same region, that have different failure domains. So things like power and networking issues, ideally they won't be correlated. If there's a hurricane, that's unfortunate. Final component to cover here is this auto admin one up at the top, which is responsible for heartbeating, doing partition health, as well as replica replacement if one of the storage nodes goes down. Okay, let's quickly go ahead and cover our single partition view. So basically, in DynamoDB, unlike Dynamo, we're actually using Paxos within a replica set, right? So for one partition, we've got a leader and we've got a couple of followers, and if one of the followers goes down, that's okay because we just need a quorum to establish a write. So 2 out of 3 is totally fine. And another thing that we do is we actually use leader leases, right? So a leader is going to basically say, hey, I am going to be the only leader for the next 10 seconds, and as a result of that, I can serve writes locally and know that no one else is going to be proposing any new writes in that time. And so as a result, you can perform strongly consistent reads by just reading from the leader. On a similar tangent, if you need more read throughput than that and you're okay with weaker consistency models, you can get eventually consistent reads from the followers, such as this guy. Okay, so how does DynamoDB go about providing this concept of infinite scalability? Well, it's certainly not trivial, but they do put a lot of thought into it, and basically the two main considerations that they ask themselves are, one, how do we deal with hot partitions or hot keys? For example, if you have a celebrity, they make an Instagram post, a lot of people are going to be loading the metadata for that post itself, and as a result, they are going to have a hot key there. Similarly, DynamoDB is multi-tenant. You've got many clients running on the same storage nodes, so if we've got one bad actor or one particular partition that is getting a ton of requests to it, how do we make sure that other partitions don't have performance issues as a result of that? Alright, so what Dynamo actually does in their original attempt is to do something called equal partition splitting, right? So the main idea here is that if I'm a developer and I want a DynamoDB table, basically I specify a provision throughput for my table in terms of read and write throughput. And then Dynamo has a hard set limit on basically how much throughput can go to one single partition. So if that limit is 1,000 and I want 3,600 throughput, that means I need 4 different partitions with 900 each. If for whatever reason I bump my provision throughput to 4,400, now I need 8 different partitions with 550 each, because otherwise we would have gone over 1,000 per partition, which is not allowed. Now there are a couple of issues with this approach, but first I'm going to go over the main pro of it, which is that if I'm a storage node and I know my individual capacity for throughput based on my CPU and my disk, I can very easily determine whether or not I can run a given partition. So if a new partition gets created, because there are a bunch of different splits, I'm a storage node, I'm potentially going to store this thing, I can say yes or no very easily, because all I have to do is look at my local state and look at the provision throughput of every partition that I'm currently holding compared to my total capacity. That being said, this strategy is really not very good for hotkeys, right? Because what if I have this guy over here, which is consuming 700 throughput of this partition that was 900 before? But then we have to split this thing. Now we've got 700, which is greater than the 550 that it gets after the split, and so now we can't really run this thing very well, and it's going to be problematic, it's going to get throttled a lot. So what we see is that customers ended up over-provisioning their tables, which is not what we want. I mean, maybe it's what Amazon wants in terms of making money from their external clients, but at least for the internal ones, you don't want them over-provisioning things. So now we're going to go ahead and talk about the first attempt that they made to improve things, which was called bursting. So basically the idea of bursting is that certain times partitions are going to have an extra amount of load compared to their baseline load, and we need to be able to accommodate that for short periods of time because it doesn't tend to last for too long. So what they do is they allow bursting to be accommodated for up to 5 minutes at one time, and the idea is basically they'll dock the amount of normal capacity that a partition has, regardless of how much you provision, and then that is saved around for when your partition has to burst. So you've got this idea of allocated capacity and burst capacity, and those are maintained by a bunch of different token buckets which live on the request routers. Now similarly, it's all good and dandy that partitions themselves can burst and have a certain amount of capacity, but you also need to keep track of capacities for the actual nodes that they live on, right? Because if a partition can burst and every single partition on a node bursts at the same time, we're going to be over capacity on that storage node. So you also need separate token buckets for the nodes themselves. Now note that while it is true that if I'm just reading from a given node, I can just look at that node's token bucket, if you're writing to nodes, you actually have to do a quorum write, and so you need to decrease the token bucket of every single node that is being written to, right? So if I did a write, this guy goes to 9, this guy goes to 19, this guy goes to 4. And the idea there is that the token buckets are just keeping track of how many requests we're able to serve within a given amount of time, and eventually they get replenished as well. The problem is, this is only for 5 minutes at a time, right? You're only allowed to burst for a couple minutes, and so what happens if you just have sustained load imbalances, right? Certain keys can be hot, and they can be hot forever. So this is where something like adaptive capacity comes in, which is Dynamo's next improvement. Basically, the idea here is that you've got some sort of global controller that is now looking at the throughput of every single partition, and if some of them are being throttled constantly, like on a request router, they'll start to actually adjust the number of tokens or requests that partition can handle, and decrease the ones with less throughput in that same table. So for example, if all these guys start out with 25, now we've got 35, 30, 22, and 13. So we're still summing up to 100, but we've got a better distribution of load per partition that accurately reflects what's going on in the system. The problem is, adaptive capacity at the end of the day is reactive, right? We have to wait for things to start throttling, wait for their token buckets to get to 0 before we really do anything. So ultimately, the final improvement that they do in Dynamo is something called global admission control. So the idea here is that we always want to let partitions burst. That's totally fine. However, the main thing is, number one, we have to be very smart about how we assign partitions to nodes. And number two is that we want to be sure that, the partitions that are bursting are getting capacity, and the ones that are not using a lot of throughput are getting less capacity as well. So in some ways, still similar to adaptive admission control, or adaptive capacity rather, but just trying to do that a little bit faster. So the way that works is we have these global admission control components, which themselves are scaled out or sharded based on the subset of tables that they're responsible for. Oh boy, my camera's up. This is fun. All right, we're going to deal with this because I just can't deal with more bullshit today. Basically, the idea here is we've got T1, so the global admission control for that. We've got T2, the global admission control for that. And they're communicating with all of the request routers. And as they're communicating with request routers, basically, the request routers are going to run out of tokens and ask them for new ones, and the global admission controller has a global view of how many requests are coming in for each partition in a given table, and as a result of that, they can basically assign new tokens to the request router in proportion to the load on each partition. Now the nice thing is on a request router, they have to go get new tokens from global admission control every few seconds or every few minutes, or they're just going to expire over time. So that is basically going to keep everything intact. And additionally, all the state on these global admission controllers is completely ephemeral, which means it's just stored in memory. If this guy were to go down, we would bring up another global admission controller, and after only a few seconds of load statistics from each request router, it could then go ahead and start to actually tip the scales a little bit in terms of which partition should be getting which load. Like I mentioned, it's great that now all of our partitions can burst as they need, but we have to be smart about how we now go ahead and handle hot partitions, right? So the idea is partitions can always burst. That being said, the storage nodes themselves are going to be monitoring their own load, because you don't want to go over that load, right? So they've got some certain threshold, maybe let's say 80% for example, where once their load goes past that threshold, they start trying to move partitions off of themselves and onto other storage nodes. So the way that they'll do that is they'll basically communicate with this auto admin component, and the auto admin component will say, okay, either I have to do some partition splitting or some partition moving, and what I'm going to do is move the extra load to another storage node in the availability zone that doesn't already hold that partition. The reason being, you don't want the same partition stored twice on the same storage node, otherwise the entire point of getting quorum rights is mitigated significantly. So one small caveat to note is that if a partition is particularly hot, but it's only due to the fact that we're hitting a single key over and over again, or it's only due to the fact that we're doing a bunch of range queries on the same key range, we don't want to actually split the partition within that range, because then you're not helping yourself out. You're just distributing a range query, which is going to slow things down. And same for the single key. Splitting things is not going to do anything well for you. You should move instead other partitions off of that storage node. So another thing to note here is that they try and be a little bit more intelligent about how they actually do partition splitting. So keep in mind, one of the problems that we saw in the past was this idea of, basically load dilution, right? So you have 900 and now we get 550 and 550, but the hot partition is, or the hot keys in that partition are getting less load to themselves. So basically the idea here is that, we can actually split partitions more intelligently, such that we make a split so that, you have even load per split as opposed to even provision throughput, but, uneven load. So that would be a problem. Okay, the final piece of this puzzle to talk about before we get into some other stuff is the concept of on-demand provisioning. So basically, the idea originally is that developers had to say, hey, I want this many read units and this many write units of throughput, and that's challenging because, what's a read throughput and what's a write throughput? Who knows? So the idea is you can just do something called on-demand provisioning instead, where you say to Amazon, hey, I just want this thing to be done on demand. You can change my throughput numbers as needed, and what it'll do is it'll just double the peak consumption and set your throughput to that. So it's just keeping metrics and keeping you in check so it scales automatically for you. Okay, another important piece of this puzzle is going to be data verification. So basically, due to hardware issues or network issues, we can have data getting corrupted all the time. We can have rotten bits or bit flips or things like that. And so the idea here is that throughout DynamoDB, pretty much any message that's being sent from one component to another, we are going to be using checksums to validate it. So examples of things that are being published and communicated are write-ahead logs on every single storage node or occasionally being archived to S3. So we use checksums on writing them and also on reading them. Basically, we've got every log entry using a checksum, every log entry in the Paxos protocol or in the write-ahead log. Every single message between storage nodes itself uses a checksum over the network. And then finally, we've got this in the background scrub process. So the scrub process is taking those archived write-ahead logs from S3 and comparing them to the write-ahead logs or the accumulated state on every single storage replica to ensure that things still look good. Okay, another piece of this puzzle is going to be failure detection. So one thing that's really expensive in a Paxos type of setup is if we've got something like a network partition right here, and then one of the followers thinks that the leader is down, so it's going to try and start a new election. However, it's not actually, it just can't communicate with the leader for whatever reason right now. So in order to try and mitigate these as much as possible, what we'll do is we'll actually have one follower reach out to the other follower to see if the leader is down. And if there's no network partition between the leader and that follower, the other follower can basically say, hey, don't start a new leader election right now. And this apparently stopped basically the majority of leader election attempts from occurring. Another thing that they do in DynamoDB to increase availability of the system is something known as Paxos acceptors. So basically the idea here is, imagine we originally have 2 database nodes for followers and one of them goes down. It's expensive to bring up another database node. The reason being that you have to go ahead and not only have all the write-ahead log entries, but then you have to apply them and iterate through them in order to build up the materialized state in the B tree. So what would be easier and brings state up quite a bit faster is if you just use something called an acceptor node, which is effectively just a write-ahead log, right? So the write that itself in the log stays durable because it's still over here in your log and you can still access it later. However, the acceptor itself is not actually building up any materialized state of what the key and value pairs look like. It simply is holding the write-ahead log, and that means we can bring one up within a couple of seconds, and so we don't have sustained replica failures. So if this guy goes down, we can put up an acceptor, and then now all of a sudden our writes are durable and we can sustain one more failure. Whereas if we couldn't bring up an acceptor and this guy went down, now we can't write at all, but one leader and one acceptor is still able to write. That's still considered a quorum. As far as software testing and monitoring does, obviously they do a ton in DynamoDB because Amazon is very, very careful to make sure that everything that they build is durable. Number one, they do things like formal testing with their replication protocol, so they have software that's actually like testing the actual formal logic of what they're doing. They're doing chaos tests where they're simulating a bunch of load. They're randomly killing a bunch of storage nodes to make sure that everything is okay, or just other nodes in their services. They have plenty of alarms and canary clients, which are basically making spoofing requests to DynamoDB, checking their response times, and setting alarms if they're bad. They've got plenty of caches for any of their external dependencies. They rely on encryption services and authentication services, and if those go down, no one can read or write from DynamoDB anymore. So by caching those results on things like request routers, they can basically ensure that if you have one of your external services failing for a minute or two, that you're still able to run just fine. What they'll also do is just asynchronously refresh those so that the cache is as up to date as possible, and that is going to again allow us to sustain a failure of an external dependency for as long as possible. They'll also just do things like rolling upgrades where they're going to roll forward and roll back their upgrades to ensure that you can do those safely in the event of bugs that they find. And then when they do so, it would be bad if you sustain downtime because the leader node of every single partition replica is still holding its lease because you can't elect a new leader until that lease gets expired. So what they'll have this do is the leader node will actually just give up its lease beforehand so that you can start a new leader election as fast as possible. And then finally, if they're ever publishing new messages in their replication protocol or just, throughout the system, they'll basically upgrade all the components to be able to read the new message first, and then they'll upgrade them to be able to write it after that. Another quick thing to touch upon is this concept of backups and restores. So like I mentioned, we've got a bunch of archived logs in S3, and what you can do with those is basically just occasionally snapshot the state of DynamoDB. All you have to do is have this periodic snapshotter component running in the background, reading those logs, building up local state, submitting a new snapshot to S3, and then doing the same exact thing where you're reading all of the next logs, creating a new snapshot, and applying them. So if for whatever reason we wanted to do a point-in-time restore to a different DynamoDB, basically all we would have to do is read the snapshot that's closest to it but behind it in time, and then apply all logs since then to get the state that we want. Okay, last thing I'm going to discuss in this video before we go ahead and conclude is going to be metadata, right? Because one thing that's pretty important in DynamoDB is saying for a given key, what storage node does this key live on? Basically, what we would do originally in DynamoDB is hold all the metadata in DynamoDB itself. So you have DynamoDB holding all of its own metadata, which is quite interesting. And the idea here is that we're performing a bunch of caching on request routers to make this as fast as possible for a client to read it. That being said, originally we were returning the entire hash ring to the router, so that's going to be pretty big. You know, you've got this whole hash ring right here, 1, 2, 3, and that's going to be expensive, especially when a new request router starts up and its cache is cold, right? So it doesn't already have the hash ring cached, meaning it's going to be expensive to refetch it again, and then we see inconsistent performance, which we don't want in DynamoDB. Another issue with this approach is if a request router goes down, we have a thundering herd on the database of all the clients who now have to go to the database to get the metadata for their tables. So instead, they try and improve this thing by building something called memds, where think of memds almost like memcached, where it's basically a horizontally scalable key value store. So memds in this case would be this layer right here. The request router is still going to be performing caching, but even if there's a cache hit, it's going to asynchronously request data from memds, so the rate of requests going to memds is always constant. So for key Jordan, what storage node does this live on? Maybe storage node 1. And then we're actually going to cache that on the request router itself. Now note that instead of sending back the entire hash ring this time, they decided to make performance a little bit better by only sending the storage node for the particular key that a client cares about. So we're just going to be caching that. Now it's also worth noting that in memds, we're not just using like a typical hash map to store our key value pairs. We're actually using something more like a binary tree. They say it's a combination of a Merkle tree and some sort of like pickle data structure, which I didn't want to go too much into because I think it's distracting. But the idea is that you can perform efficient floor and ceiling queries, which if you think about it, is going to allow us to quickly find the node that a key corresponds to in a consistent hashing ring. That being said, even though memds is very nice, it's ultimately not the source of truth for where given keys live. The ultimate source of truth is going to be DynamoDB itself. And so it is possible that memds is going to receive an update from DynamoDB. That's going to be stale because maybe the partition moved to a different storage node in the meantime. And then if that thing is stale, then the client is going to send the request to the wrong place. In this event, the DynamoDB node is just going to forward that request to the right DynamoDB node, so it's not really a huge deal at the end of the day. All right, let's go ahead and conclude this thing. I'm sorry I'm speaking so fast. It's been 5 times doing this. I'll remake this video if I have to, but yeah, just brutal one. Anyway, point is DynamoDB is trying to combine Dynamo's performance as well as SimpleDB's usability from a developer and operational perspective. It's completely managed, and additionally, it gets consistent performance. The reason we get consistent performance here is because we're taking tons of care to move around partitions such that those that are getting tons of throughput requests on them, or just require tons of throughput, are getting the capacity that they need. And in addition, they're doing all of this caching on external services and trying to keep the number of requests on every single external service as consistent as possible in order to basically accurately model the type of load that they're undergoing. So even if they have an external dependency that fails, they can still hold on for a couple of minutes at a time. Anyways, guys, I hope you enjoyed this video. I'm sorry to have rushed through it, but yeah, it was better before, I'll say that much. So I'm really hoping my iPad doesn't corrupt this one. We're about to see.